Everybody, and welcome to a new video on the mobile robot localization. Today we are going to discuss particle filters. And now particle filters are actually a quite modern approach, and it's being used extensively nowadays in localization problems. Now this is going to be a first part using the known data assignment assumption. Now the table of contents. First, I'm going to give an introduction of what are particle filters. Then I'm going to discuss importance sample, which is one of the basic building blocks of a particle filter. Then I'm going to describe a basic particle filter localization algorithm. And to really exhibit the power and the distinctiveness of a particle filter, I'm going to discuss the kidnapped robot problem, which was the third, in our hierarchy of localization problems. Then I'm going to discuss how we could modify the vanilla particle filter to solve this kidnapped robot problem. And finally, I'm going to show the results of applying this algorithm to a fictitious map. Now first, what are particle filters? Basically, first of all, particle filters are a type of non-parametric filters. So this means that when a particle filter is trying to approximate a certain density, it does that using samples from that probability density. Now this is in contrast to the EKF type of filter or the Kalman filter in general, because these try to approximate the density or the posterior using Gaussians, which means that we are going to parameterize the Gaussians using the mean and the covariance matrix. Particle filters, on the other hand, use samples from that type of distribution along with weights corresponding to each sample. So as we said, we approximate the posterior using a set of weighted samples. Now the following figure might show a typical type of how particle filter works. Now you can see that at the beginning of the localization, the particles are spread, then they focus on the robot position as it progresses and incorporates more measurements into the into the sensing range of the robot. Now we're going to put these kind of ideas into more concrete terminology. We're going to discuss something we call importance sampling, which is one of the basic building blocks of a successful particle filter. Basically, the idea of importance sampling boils down to that we are trying to approximate a certain distribution f using a bunch of samples. However, sampling from f could be quite costly or sometimes even impossible. However, we do have samples drawn from a distribution G, which could be simple, like a Gaussian or a uniform distribution. And the idea is that we are trying to use these samples to approximate f, although they are drawn from G. So the idea is that we weigh those samples with weights that are proportional to f over G. So this really means that in areas where the G is actually quite low and f is quite high, we're going to give those samples a large weight. And those where G is super high and f is low, we're going to give them small weight because they do not correspond quite well to f. So in this case, this is how the samples would look like. These are the samples that we used earlier. However, the length of the line now reflects the weight. You can see that the weights here are high because they are in places where values of f are high and values of g are low, and the opposite is actually quite here. And now we're going to discuss a full basic particle filter localization algorithm. Now, as we're going to see, particle filter is probably one of the easiest to implement so far, as the ones that we have discussed, which was the EKF-based localization. We can see that the particle filter has two loops. Now, in the first loop, we're going to loop over the particles. M, big M, is the total number of particles. So first, we're going to predict each particle by sampling from the motion model. So we have xk minus 1 m, that's the mth particle from the k minus 1 step. Now we are going to sample from the motion model based on this previous state the motion command control, and the alphas that we have chosen to represent the motion model noise. Now, of course, if this terminology seems vague, you can go back to my first EKF video where I discussed in length the motion models and how we represent it. So this serves as a prediction step. Okay, so we are sampling from this distribution, the motion model distribution. And now we are going to compute weights. These weights for the mth particle at the time step k would have to be something about related to the measurement probability given the measurement matrix Z and the state xkm. So this actually tells how well does the measurement matrix Z fit the the predicted measurement that can be seen at this state. So this would serve as a weight to that sample. So the higher this probability is, of course, that's actual probability, it's more like a likelihood because it's based on density values. So the higher it is, the more agreement there is between the matrix Z and the measurements read at, or predicted really, at xkm. So this is the weighing process. And now we go to the final step, which we call the resampling. Okay, so again, we go through F4, through all the number of particles. What we do is that now we have the weights, so we redraw the particles, okay, with probabilities related to these weights. So now we kind of have a discrete distribution made of the weights, okay, from 1 to m, and we just try to sample in accordance or in proportion to those weights. So this serves to, to relocate or refocus the particles to high probability regions, and actually has the effect of trying to approximate the posterior of the states after incorporating the measurements. So this is the resampling step. It's actually quite crucial in a particle filter. As you can see, these steps are actually quite easy and quite simple to write, which makes the particle filter a powerful localization algorithm. And now we're going to go one step further. We're going to discuss the kidnapped robot problem and how the particle filter is actually now one of the first algorithms that we discussed here that could actually tackle this kidnapped robot scenario. Kidnapped robot problem is a sudden and unpredicted change of the robot's position. So this could happen because maybe the robot got, hit by an obstacle, maybe got kicked by a certain human in the environment, any kind of sudden type of failure mode that causes the robot to change its position without it trying to command that change. So really would be really quite easy to solve if it is diagnosed correctly. So basically this would look like a global localization problem because we just simply reinitialize the filter, in our case the particle filter, having particles spread all over the space, and then we wait for the convergence. That would be quite easy, but the problem is the diagnosis. So we need a kind of a tool to measure how good the localization process is going. So this would be a topic that we're going to discuss quite shortly. Now, just to get a feeling of what the kidnapped robot problem looks like, now here to the left, we have a particle filter with particles being represented by these green dots. We can see that the particle filter has converged to a certain robot location quite here. The problem, however, is that the robot has been moved to this location. So the particles are quite focused here. They believe the robot is here, but now the robot is in a different place. So the idea is that if we could correctly diagnose this kind of failure mode, we could just redistribute the particles. And after a few iterations, they could just refocus on the new robot location. And that's what we are going to discuss in the next slides. So now we're going to talk about solving the kidnapped robot problem, the KRP, and how we're going to modify the vanilla particle filter to do so. So the main observation is that the vanilla particle filter cannot solve the KRP because, once the particles are concentrated on a certain place, there is no way to redistribute the particles randomly in the space. So as we said, we need a type of a metric to evaluate how the localization performance is going. Now, in a particle filter, it can be shown that the mean of the weights, omega AVG, okay, of all the particles at a certain time step is kind of equal, is a good approximation of the measurement likelihood. Okay, so the measurement likelihood would say how much does the measurements at the current time step correlate well with what we saw earlier and the motion commands and the map. So this would serve as a good idea or as a good metric to measure how well we are doing the, the localization process. Because if we start seeing gibberish kind of measurements, then that means that we have completely lost our sense of location. Now, one slight problem is that omega AVG does not always be small when there's failure. It could actually be quite low at the beginning of the localization. So this might cause us to have a false detection of failure and just keep redistributing the particles randomly. Okay, so it's not quite a robust method, but it's quite simple to do. So one idea is that we keep track of two smoothed versions of omega AVG. We call them omega slow and omega fast. So omega slow is a long-term average of this kind of this quantity right here, and omega fast is a short-term average that quickly adapts to the violent changes in omega AVG. So the idea is that omega slow would reflect how this kind of measurement likelihood was evolving on a really long time step or long term, like for several tens, hundreds of time steps to the past. Omega fast, on the other hand, adapts quickly to the violent changes in omega AVG. Now, actually, if we have omega fast that is way smaller than omega slow, so this means that when we can see that the instantaneous average, the instantaneous measurement likelihood is quite low compared to what we have been seeing for the last few iterations on a long-term basis, this would mean that we suspect that failure occurred. So this is actually quite a simple idea because we are comparing the instantaneous metric of performance to the long-term metric of performance. This would allow us to overcome the problem of false detections of failure at the beginning of the localization. And now we're going to modify the vanilla particle filter to kind of solve the KRP problem using the ideas that we just discussed. So basically, first of all, we do the first loop, we do the prediction, as we said, we do the weighing, and after this loop, we kind of compute the average of those weights, and we compute the omega slow and the omega fast, which are the smooth versions of the average. You can see here that the omega slow is computed using a parameter called alpha slow, and this one is computed using something we call alpha fast. Now, it should be true that alpha slow is way smaller than alpha fast. Now, it can be shown if the expression is remanipulated that omega slow adapts really slowly to the changes in omega AVG, as we can see, because it's multiplied by alpha slow. Alpha fast or omega fast, on the other hand, would adapt really quickly to changes in the average value, which is what the desired effect actually is. That is the average computation step. Now, the core idea of this modified particle filter would appear in the resampling step. So basically, we're going to draw a random particle with probability that is actually proportional to 1 minus omega fast on omega slow. Now, as we mentioned, when we suspect that there is failure, omega fast would be considerably lower than omega slow, which would mean that this expression right here would be super close to 1, meaning that we are going to start drawing random particles with a higher probability. On the other hand, when omega fast is bigger or equal to omega slow, then we're going to have 0 probability and there will be no random particles. So either we draw a random particle with this probability, or we just draw a particle with probability that is proportional to the weight distribution that we just talked about. So basically the filter keeps its normal performance when there's no failure and tries to spread or inject more random particles when we suspect that there's failure. Now this is the resampling step, as we just said. Finally, we're going to show the results when applied to a fictitious map. So this right here would show the nominal path of the robot in a landmark map. The landmarks are given by red dots. The robot is in this kind of, pink color. Sensing range is in green, and the blue dots are the nominal path of the robot. Now, first, we're going to do a global localization test. That is, we are not going to assume that the robot has been kidnapped. So you can see that the real path is given in black here. Now this is due to the motion noise, sorry, and this has caused a deviation from the real path. So you can see that if we just use odometer data without any filtering, we would end up somewhere quite far and quite different from where the real path actually takes us. So now this right here would show the result of the robot path given by the particle filter, which are the red dots, and the real path, which is given in black dots. You can see that the particle filter did an amazing job in estimating the real robot path, and it actually did so quite quickly in practice as I was trying to code up the particle filter. Now remember, this is the vanilla particle filter. It was really easy to code, and it actually took super fast times because the update steps are actually quite quick. Now this here would also show the angular estimation error. You can see that it reaches a peak of maybe 8 or 9 degrees, towards on the whole time of the simulation. Now you can see that the particle filter has really excellent performance, and it's quite easy as compared to the EKF based localization filters. So now we're going to move to the kidnapped robot test. So the figure here would show quite many complicated paths. So let's try to unpack that. So you can see that the robot starts here. Now it moves according to the first phase, which is the black curve, right up to here. Then our scenario is that the robot is kidnapped and thrown right back at the beginning. And it just follows a different path, which ends up after the red dot. Now the blue one would show what the robot would actually do if it only believed, or what the robot would think it would be, if it only believed its odometry. So it would just go here, end up here, and then just completely integrate the command or the motion model. It keeps integrating that right up until here. So it ends up in a quite far place from where it actually is. So now we're going to see how the particle filter would be able to recover from such a failure mechanism that the robot has been reassigned and relocated. So remember that the particle filter would have been converged at the end of the first phase. All the particles would be focused here, and then it has to re-inject the particles randomly and then to refocus them on the correct position. So we have used an alpha slow, a really small alpha slow, 0.301, and alpha fast of 0.9999. So the figure here would show how the first phase of the localization went. You can see that the first phase was actually quite successful. The filter has completely converged. Now the second phase, you can see that at the beginning the particles were distributed quite randomly because it had detected the failure. After that, a few time steps, it was able to catch up with the real path and was able to converge. So this shows that a simple modification on the vanilla particle filter was able to overcome the kidnapped robot test, which is quite a powerful method and quite easy to code up and to test. I should mention that actually calibrating AlphaSlow and AlphaFast was not quite easy, but the whole method is simple to implement and easy to understand and interpret. Now for some final thoughts. So we could just, future ideas, we could try grid-based filters. Now these are also able to, represent arbitrary types of, distributions, just like the particle filter. I'm not sure they gained that much traction. They actually used quite a lot in occupancy grid maps and other types of, map representations. The only problem is that they're actually quite costly, but we could try to cut them up and see how they compare to the particle filters and the EKF-based localizers. Second, you could actually, as usual, you could use more sophisticated sensor models like the LiDAR, in which case we would have to represent our map using a polygonal map, and just try to match the blind segments that we extract from the LiDAR to what we actually see. Now, this could be a more realistic scenario, and this might be a video that will come out soon, hopefully. Now, we could also model misdetections, spurious measurements, in which case we have, random landmarks popping out of nowhere, misdetecting existing landmarks, these types of sensor models. Of course, the most important idea is that the failure detection mechanism in the current particle filter might not be that quite robust. It might work most of the times, it could fail, it might detect the failure in a not so correct situation, which could lead to failure in localization. Now, of course, there could be other robust methods. We will try to look into this idea also. And of course, relax the known data assignment assumption to go to a more realistic case. So thank you very much for listening. And as usual, if you have any comments, ideas of what I could do to make the videos better, or if you would like to discuss more deeply into the coding part, which was done on MATLAB, I could also make a few videos on those. And yeah, I'll be happy to interact with you guys in the comment section. And that's it. Thank you very much for listening.